Alright, section 7.3, proving that a quadrilateral is a parallelogram. Our objectives are to identify and verify parallelograms. And our essential question, how can you prove that a quadrilateral is a parallelogram? We need to start with our theorems. And the theorems for this section are the converse of all of the previous lessons' theorems. Essentially switch the hypothesis and the conclusion. So take a moment to copy down all of these converse theorems to previous lesson theorems, in addition to the implied statements. All right, now we're going to use these properties to help us solve and determine values of x and y to change the quadrilateral to a parallelogram. So as you can see right now, it doesn't quite look like a parallelogram, so we want to know what values of x and y would change the quadrilateral to look more like a parallelogram. So we're dealing with some diagonals here. We know that diagonals bisect each other. So we can set up two different equations to help us solve for x and y separately. So first we can say that 12x minus 17 equals 8x minus 5. Each of those segments have matching tick marks. Our second equation, set up with the second diagonal, we have 5y plus 8 equals 4y plus 10. Each of the segments have two tick marks, matching tick marks. Therefore, they are equal. So now just solve for x. All right, and so we get, when we combine like terms for the 12x minus 17 equals 8x minus 5, we get 4x equals 12. Then we divide both sides by 4, x equals 3. For 5y plus 8 equals 4y plus 10, we combine like terms, and we get y equals 2. So in order for this quadrilateral to change to a parallelogram, x must equal 3 and y must equal 2. Next, let's take a look at a parallelogram, opposite sides converse proof. We're given that segment AB is congruent to segment CD, and that BC is congruent to DA. We want to prove that ABCD is a parallelogram. So let's start with a sketch. Here we have parallelogram ABCD, or what we think we want to prove that it's parallelogram. So we know that we're given AB is congruent to CD, so let's mark our picture. And then also construct a diagonal from A to C. So our plan is that we'll construct this diagonal, and we'll ultimately want to prove these two different triangles congruent, and then we can use the alternate interior angles converse to show that the opposite sides are parallel. So let's start our proof. We start with our givens. We'll do a 2-column statements on the left, reasons on the right. And we're given AB is congruent to CD and BC is congruent to DA, reason given. And then we drew in diagonal AC, and we can do that because of the reason that 2 points implies one line. From there we can conclude that AC is congruent to CA, and that's because the reflexive property of congruent, so any two triangles that share the same side means that that side is always going to be congruent to itself. And there's going to be enough parts. We have 3 separate pairs of sides to prove that the triangles are congruent. So now we can say that triangle ABC is congruent to triangle CDA. Reason, side, side, side implies congruent triangles. And then from here, all remaining parts are congruent. So the parts that we need to be congruent are angle BAC, congruent to angle DCA, and also angle BCA, congruent to angle DAC. And our reason is congruent triangles implies congruent parts, or in other words, CPCTC. And because we have alternate interior angles congruent, then we can conclude that segment AB is parallel to CD, and that segment BC is parallel to DA. Reason, alternate interior angles congruent implies parallel lines. In other words, this is the alternate interior angles converse theorem. And since we have opposite sides parallel, we can conclude that ABCD is a parallelogram. both pairs of opposite sides parallel implies parallelogram. This is the conclusion of our proof because we wanted to prove that ABCD is a parallelogram. Next, let's take a look at this example where we have an amusement park ride that has a moving platform attached to 4 swing arms. The platform swings back and forth, higher and higher, until it goes over the top, around in a circular motion. In the diagram, we see that AD and BC represent 2 of the swinging arms, and DC is parallel to the ground, which we'll label line L. Explain why the moving platform AB is always parallel to the ground. Since the nature of the ride is such that the swinging part maintains congruent opposite sides, we can conclude that the shape of the quadrilateral ABCD changes as the moving platform swings around, but its side lengths do not change. Both pairs of opposite sides are congruent, so ABCD is a parallelogram by the parallelogram opposite sides converse. So by the definition of a parallelogram, we can say that segment AB is parallel to segment DC, and because segment DC is parallel to line L, by the transitive property, we can say that segment AB is also parallel to line L. So the moving platform is parallel to the ground. All right, our next example has us setting up equations again. So finding side lengths of a parallelogram for what values of x and y is quadrilateral PQRS a parallelogram. So again, we're going to use our properties. So we know that x plus 9 opposite of 2x minus 1 must be congruent because opposite sides are congruent of a parallelogram. And then y equals x plus 7. So our first equation will yield a value of x equaling 10 when we solve for x. So 2x minus 1 equals x plus 9. Solve for x by combining like terms. And then once you have that value of 10, you plug that into the expression for the y equals x plus 7. So we can plug in 10 for x, and that yields a y value of 17. So when x equals 10 and y equals 17, the length of PS is 17, and the length of QR is also 17. So quadrilateral PQRS is a parallelogram when x equals 10 and y equals 17. All right, and then our last 2 theorems for this section. If one pair of opposite sides of a quadrilateral are congruent and parallel, then the quadrilateral is a parallelogram. Second, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. And then you have your 2 implied statements. All right, so let's take a look at example 3. The doorway shown is part of a building in England. Over time, the building has leaned sideways. Explain how you know that the length of SV equals the length of TU. Well, we can see in the photograph that ST is labeled with an arrow, and opposite of that side is VU, also with a single arrow labeled, implying that they are parallel. So in the photograph, we can say that segment ST is parallel to segment UV. It also has congruent marks, matching congruent marks on those 2 sides, so we can say that ST is congruent to UV. So by the opposite sides parallel and congruent theorem, quadrilateral STUV is parallelogram. By the parallelogram opposite sides theorem, you know that opposite sides of a parallelogram are congruent. So we can conclude that the length of SB is equal to the length of TU. Next, we want to look at finding diagonal lengths of a parallelogram. So for what value of x is quadrilateral CDEF a parallelogram? So again, we see labels for the diagonals, and we know that if the diagonals bisect each other, then the quadrilateral is a parallelogram. So what we need to show is that these diagonals do indeed bisect each other. So if they bisect each other, we can say that 5x minus 8 equals 3x and solve for x. So by the parallelogram diagonals converse, if the diagonals of CDEF bisect each other, then it is a parallelogram, as stated a moment ago. So we set up 5x minus 8 equals 3x and solve for x, so x comes out to equal 4. So when x equals 4, Fn, length of Fn equals 5 times 4 minus 8, which equals 12. And the length of Dn equals 3 times 4, which equals 12. So quadrilateral CDEF is a parallelogram when x equals 4. Alright, pause the video here and try numbers 2 through 6 on your own using all of the converse properties. And then unpause to check your answers. Alright, check your answers. For number 2, x equals 32, y equals 29. For number 3, opposite sides parallel and congruent implies parallelogram. For number 4, opposite sides congruent implies parallelogram. And then for number 5, opposite angles congruent implies parallelogram. And for number 6, x must equal 2. All right, for our final example, we'll look at using the coordinate geometry, so identifying a parallelogram in the coordinate plane. Show the quadrilateral ABCD is a parallelogram. So knowing that opposite sides parallel, opposite sides congruent, and we're in a coordinate plane, you got to know that we are definitely going to be using two special formulas. Our distance formula to find length, in other words, in order to find the lengths of each sides, and then slope whenever we're trying to prove opposite sides parallel. So first we want to show that the pair of sides are congruent and parallel. Then apply our opposite sides parallel and congruent theorem. So first use the distance formula to show that segment AB and CD are congruent. So we plug in all the numbers, the coordinates, x and y coordinates for A and B, and get a length of square root of 29. Do the same thing for length of CD, and we find out that it is the same, so square root of 29. So because AB equals CD, which is square root of 29, we can conclude that segment AB is congruent to CD. Then we use the slope formula to show that segment AB is parallel to segment CD. So we use our slope formula, and we get slope of AB is 2/5. We use our slope formula to find CD slope, and it is also 2/5. So AB and CD are congruent and parallel. So quadrilateral ABCD is a parallelogram by the opposite sides parallel and congruent theorem. Our second method could be that we show that opposite sides are congruent, both pairs of opposite sides. And that would be, we would apply the parallelogram opposite sides converse. In method 1, we already showed that AB equals CD, which equals square root of 29. Therefore, segment AB was congruent to segment CD. Now we want to find the length of AD and the length of BC. In order to do that, we're going to use the distance formula once again. So we plug in all our x and y values for each of the vertices. And we get for the length of AD is 3 square root of 2. Do the same thing, plug into the distance formula to find the length from B to C, and we discover that the length from B to C is 3 square root of 2. So because AD equals BC, which equals 3 square root of 2, we can conclude that segment AD is congruent to segment BC. So since both pairs of opposite sides are congruent, we proved or showed in the first method one set of opposite sides congruent. Here in the second method, we showed that the second pair of sides are congruent, so quadrilateral ABCD is a parallelogram by the parallelogram opposite sides converse. The end.